Hi, welcome back to es346 Basic Thermodynamics. This is module 6.1 on the second law of thermodynamics. The sections in the textbook are 6.1 to 6.2. Let's look at our overall course outline, and we're now moving into the third part of the course where we're going to begin discussing the second law of thermodynamics. This module corresponds with chapter 6, where we'll be focusing on the Carnot cycle and some qualitative examples of what is the second law. When we go to chapter 7, we'll introduce the concept of entropy, which is a way to quantify the second law of thermodynamics. And then in the final chapter, we'll discuss exergy, which is actually a combined property for both the first and second laws of thermodynamics. Here are the two learning outcomes for this module. At the end of the module, you'll be able to describe what we mean by the second law of thermodynamics, and you'll be able to characterize a thermal reservoir. So, here's a definition of the second law of thermodynamics that I often use. And it says, some processes can only occur in one direction. And I like to think of what processes you might be talking about would be, for example, an energy transformation. So let's look at one of those. Imagine here I have a resistance coil, and if I was to run an electrical current through there, I would effectively be supplying it with some electrical work. As it runs through this resistor will heat up, and it will give off some heat, Q. And so what I'm doing is an energy transformation of turning electrical work into heat. That process occurs all the time. Now, however, if instead I was to go ahead and add heat to this, so I just take the heating element and stick it in my oven, for example, and heat it up, I would not find that there would then be an electrical current coming back out of this. That does not happen. So there is an energy transformation that satisfies the first law, but doesn't actually happen in reality, and so it doesn't satisfy the second law of thermodynamics. Here's another example. It's very closely related. This is a picture from the textbook. And if I was to go ahead and have this weight, and it's connected to a bar here with a paddle wheel inside, release the weight so that it can go ahead and move down, it would cause this paddle wheel to spin. And if this box is well insulated, the energy from the potential energy of this block would turn into thermal energy inside here, inside my tank, and it would heat up. But if I were to do the reverse, if I was to go ahead and add some heat into the system and try to get this block to go up, I wouldn't be able to do it. So again, although I could balance the amount of Q with the amount of potential energy here, that process doesn't occur. And it's another one that doesn't happen due to the second law of thermodynamics. So we've looked at some processes that don't occur, and it's good to kind of think of some, well, that may occur. And that introduces this concept of reversibility. And we'll talk a lot about that when we discuss the second law of thermodynamics. And a classic example of a reversible system is a pendulum. And you can imagine this pendulum is swinging back and forth like this. And for now, we'll go ahead and assume that it is frictionless. And so what this pendulum is doing is it is converting potential energy into kinetic energy when it's down here at the bottom. Then it goes back into potential energy, and then if it goes and swings back and forth, neglecting any air friction, this could go on forever. And we're doing an energy transformation. We're transforming potential to kinetic, and then kinetic to potential, and again. So this is a process, an energy transformation, that does occur in both directions. So therefore, this is a reversible process. And we'll talk a lot about that, as I mentioned in the second law. So one of the things you may have noticed from the discussion of the irreversible processes on the previous slide and reversible processes on this slide is those that involve Q going into W are the processes that seem to not occur in the reverse direction. And that's absolutely true. And that's what the second law really deals with, is energy transformations that take disorganized energy, thermal energy, which we usually symbolize with Q, trying to turn it into organized energy, such as W. We can't do the reverse process with 100% efficiency. And that's really getting at the second law of thermodynamics. So, here are the two laws of thermodynamics. First part of the class, we've been looking at the first law of thermodynamics, and it said that energy was conserved. Now we're talking about the second law of thermodynamics, which says some processes cannot occur, and we can also expand that further and say that all processes can only occur with a certain efficiency. So one of the concepts that we'll use a lot is this concept of a thermal reservoir. And so I kind of want to explain what we mean by a thermal reservoir. So imagine that I've got some large system here, and it's at some temperature T. And if I was to go ahead and add some energy to it, energy Q, we would often write our energy balance to say that Q is equal to M C sub P delta T, where delta T is a change in temperature of this system that I've drawn here. Now, if my system was very large, so it had a very large mass and a reasonable heat capacity, such that this term of MCP was very, very large, MCP is large, for a given amount of Q, I would end up with a small delta T. And so as this term here gets larger and larger, delta T is going to get smaller and smaller to some point at which T is essentially constant. So we call a thermal reservoir something that has a very, very large MC term. And therefore, we can add energy to it, Q, or even remove energy from it, and the temperature will more or less remain constant. And so let me give you a couple real physical examples of things that function as thermal reservoirs. Here I show a burner. And this burner has a particular temperature. If I were to put a thermometer here, I could measure what the temperature of this is. However, it's still continuing to supply heat, supply Q, but its temperature doesn't change. So it's more or less functioning as a thermal reservoir because its temperature remains constant, although it's able to go ahead and supply a given amount of heat Q without getting any colder. Another example of a thermal reservoir on the other side would be, for example, a lake of water, and it's very large. I could go ahead and dump a whole lot of heat into this Q, and I would really not change the temperature of this thermal reservoir here. So this would be a thermal reservoir that's at a lower temperature, T sub L. This would be a thermal reservoir that's at another temperature, T sub H.